Okay, so today we're talking about rational roots. So how many roots? So first let's talk about how many roots an equation have. So look at the largest degree of that term. Like the last lesson or one of those lessons we learned about end behavior, right? Uh, if this is an x squared graph, how many solutions will you have? Well, it's kind of obvious. You're going to have two solutions. It doesn't mean they're both going to be rational, but you'll have two roots or two solutions. So roots is kind of the same name as solutions, just a different word for solution, which is where essentially where the graph is going to cross the x-axis if it's a real solution. So like there and there might be the real solutions for that problem there. So let's talk about the next one. So this one is x to the third. You know the end behavior. The graph's going to look like this. Might have some wiggles in between. But it's going to have a total of three solutions. That should not surprise you, right? It's x to the third power, there'll be three solutions. It doesn't mean they're all real. Like it's possible the axis is here, right? And the only places it crosses is one spot. But maybe the axis was up a little bit. If that was the case, this graph was down. Now you'd have three solutions there on the axis. So it just kind of depends. But definitely three solutions. I don't know what type of solutions yet, but I know there are going to be three solutions. That's the key on this, is knowing how many going in. X to the fourth, so there will be four solutions. If you want to say that in words, the theorem, you can write that down, is that every polynomial equation with n roots, n degree, has n solutions, which is basically what we did. Third degree, three solutions. Fourth degree, four solutions. Pretty simple concept. This is a very intimidating theorem, so it's called the rational root theorem. Let's remind ourselves what rational numbers are. So rational numbers are numbers with fractions. So when the solutions are a fraction, or could be written as a fraction, so even if the solution was 5 or something, like that could be written as 5 over 1, that's nice and rational. Maybe a solution is 1/3, that's nice and rational, right? So any kind of fraction, which, by the way, would mean a repeating decimal, right? Repeating decimals are really fractions. Or if you had something like x equals 1.5, you could write that as a fraction because it's a terminating decimal. It's 3/2. So lots of nice, I call these like nice solutions. So when you have rational solutions, you're not talking about solutions like square root of 5, right? That's not a nice number. If you look at the decimal for that, oof, right? It's never ending. It doesn't have a pattern to it. It's not a nice number. Okay, so let's try to at least figure out what this theorem is saying. And I don't think you have to fully write this down even. By the way, this is supposed to be, the notation there is a sub n minus 1. So n minus 1 is a subscript of a there, which is like in parentheses here. So a sub n minus 1. So this is a pretty intense theorem. Here's the concept you need to get from this. And this is the big thing that you need to get from this, which is the last term goes in the, so let's see, factors of, let's see, a sub 0, p is an integer factor of a sub 0. So p goes on the top. The factors of that one go on the top. The first term, the factors of that one go on the bottom. So that's the key. You want to factor both the first and last term. So when I say the first and last term, here's what I mean. I know this is a lot of gibberish there. So what it means is this. Let's say you have something like this. Y equals -4 times x to the third plus 3x squared minus 2x plus 1. So for this problem, what that means is you take the last term, right? Factors of the last term go in the numerator. Factors of the first term, as in the leading coefficient there, go in the denominator. So you factor 1, all those factors go on top. Well, it's just 1. Factor 4, so the denominator is either 1, 2, or 4. Those are the only factors that multiply to make 4. 2 times 2 is 4, 1 times 4 is 4. So 1, 2, and 4 are the denominator, and that's where you would list out the possibles. So in this case, the possibles would be 1/2, 1/4, and 1/1, which, by the way, 1/1 is just 1. So 1/2, 1/4, or 1 there would be the three options that you could have. These list you the possible rational roots. So you probably want to write that somewhere. It lists all the possible rational roots. It doesn't mean any of those, 1/2, 1/4, or 1, are actual solutions. In fact, I don't know if any of them are. So let's graph our calculus just to find out if any of those are actual solutions. So we go to new graph page, -4x to the third plus 3x squared minus 2x plus 1. And it looks like there's a solution there. Let's go menu 5.1 right there, 0.606. And by the way, if I kind of hover, it shows me more decimals of that number. If I hover, hit the plus sign, wow. That doesn't look like a nice number. It showed me like the first 10 decimals or something like that. And they just said, is that enough? It won't show me any more. That looks like an irrational number to me. So even though these are the list of possible, 1/2, 1/4, and 1, those aren't any of the actual solutions. So this theorem does not list all of the rational solutions. It lists all the possible rational solutions. So let's try it on this one to see how this works. So I guess this one, let's just do factors of the last term go in the numerator, right? So this will be 3 and 1. Those are all the factors of the last term. Factors of the leading coefficient go to the denominator, 2 and 1. And so what we're going to find is all the possible combinations of those two numbers. So one possibility is 3/2. So 3/2 is a possibility. Technically, I guess I didn't say this last time, all of these could have been plus or minus. Possibly. None of them are, but all of them could be either positive or negative. The reason for that is when you multiply, for example, 1 times 1 is 1, but also -1 times -1 is 1. So keep that in mind, that all of these are going to be plus or minus because factors of 3 and 2, that you could have negative times negative is also positive. Let's do other factors with 3 in the numerator, so that would be plus or minus 3. Factors with 1 in the denominator, that'd be plus or minus 1/2. And factors with 1 also would be plus or minus 1/1, which is 1. So there are actually 8 possibilities listed here. 4 possibilities, but all of them are plus or minus. So if there's 8 possibilities, those are the possible rational zeros. It doesn't mean any of them are. Let's graph it and see. So I don't know if any of those are. Let's see. So 2x squared. Oops. 2x squared plus 4x plus 3. Whoops. It helps not to write it all in the exponent spot here. 2x squared plus 4x plus 3. There we go. So it looks like this doesn't cross the x-axis at all, so it doesn't have any real solutions. It only has a couple of imaginary solutions. It would have 2 solutions since it's degree 2. So none of these are actual solutions. Those are just the possible rational solutions. If there are rational numbers, it's going to come from one of those, if there are rational solutions. Well, I'm hoping this one works out better. Let's try this one. So factors of the last term, that would be 3 and 1. Again, all of these are going to be plus or minus. And then factors of the first term would be 2 and 1. So if you want to write out all the possible, that would be plus or minus 3/2, plus or minus 3/1. Is this the same problem? Pretty much end up with the same answers, don't they? Plus or minus 1/2, plus or minus 1. Let's see if this one actually does work out. So we get the same list of possible rationals. So if I graph 2x squared plus 5x minus 3. Ooh, this one does have solutions. So let's see. Menu 5.1. Looks like 1 at 1/2. That's one of our possibles. And 1 at -3. So there are 2 solutions here. And it shouldn't come as a surprise that one of those solutions is -3. Whoops, the highlighter. I thought I had that. There we go. -3, which is -3 is that one. And one of the solutions is 0.5, which that's positive 1/2. So we see that we have two rational solutions for this problem, and guess what? They were on our list of possible rational solutions. There was no way this graph was going to cross at somewhere like, 1, 2, 3, 4, 5, 6. It's not going to cross there. Why is it not going to cross there? Why does that not make sense? Why is it not going to cross there? Because 5 or 6 is not one of our possible rational solutions, so it does not cross at 6. There's no way. The only place it could cross is these 8 spots, but it only crossed in 2 of those because it's x squared. So both of those were rational solutions. Okay, factors of the last term, I'm going to put in the top of the numerator. So the numerator 16 plus or minus 8 and 2, 4 and 4, 1 and 16. Those are all the possible, I didn't put them in order, but all the possible factors of 16. Now let's do all the possible factors of 1. Well, that's easy. The denominator is only 1. All the list of all the possibles, these are all going to be over 1. So plus or minus 16, plus or minus 8, plus or minus 4, plus or minus 2, and plus or minus 1. So this is the list of all the possible rational zeros. If there's a rational zero, it's going to come from the list, that list. I'm positive about that. I don't know if any of those are actually solutions, but I know it's going to come from that list if there are nice rational solutions. So I guess this is x cubed. Let me do it so I can read it. So let's go to a new graph page. X to the third minus 4x squared plus 4x minus 16. So it looks like it only crosses once there. It crosses at 4. So it looks like 4 is one of those solutions. So here's where we use so we found one of them is 4. So I know there's a solution at x equals 4. So when you find one, what I would do is combine what we learned the other day. So let's synthetically divide that out. I know there's a solution at 4. My coefficients here are 1, -4, 4, and -16. The nice thing is I know the remainder is going to be 0 because I know that's a solution. So bring down the 1. 4 times 1 is 4. That's 0. That's nice. 4 and 0 is 4. 4 times 4 is positive 16. My remainder is 0. No surprise. That's the constant. That's the x term. That's the x squared term. So we get as our answer, or at least our other factor here, would be x squared plus 0x, which I don't really have to write, plus 4 equals 0. So I know one of my solutions, but I've got to find the other two. And so to solve this, it looks like we want to kind of get that 4 to the other side. So x squared equals -4. Take the square root of both sides. So square root of both sides, don't forget, plus or minus. And hopefully that is not a tough problem for you at this point. So you got x equals plus or minus. Square root of 4 is 2. Square root of negative is I. So that would be plus or minus 2i. Would be your other two solutions. So there are 3 solutions. I expected 3 solutions because it was a cubic. But what I might not have expected is 2 of the solutions are imaginary. Although if you look at the graph, it makes sense, right? Only one time does it cross the x-axis there. So you've got 3 solutions, 2 imaginary, and this is the only real one right there. List all the possible roots. Again, kind of an easy one just because that value is 1. So factors of 15, 15 and 1, 3 and 5. All those are plus or minus. Factors of 1 in the denominator. So the values you get are here, plus or minus 15, plus or minus 5, plus or minus 3, plus or minus 1. So you have 8 different possible answers there. So again, we're going to try to graph this and find some of those possible rationals. I really don't want to, if any of these are irrational, I don't want to list those out. I only want to get from the calculator the rational ones. I like getting exact answers. If it says the answer is 0.231 or something, I'm not going to really bother with that particular solution. So I want the exact answers in this case. So x to the fourth minus 4x to the third minus 8x squared plus 15. Looks like it does have 2 solutions. Let's see, 2 real ones anyway. Menu 5.1. Now let's see. There's a solution. And there's the solution. This doesn't look good, does it? $5.39. If I hit plus sign there, I get some more digits. If I hit plus sign here, ooh, this is rough, isn't it? So none of these are nice, real, rational solutions. So find all the roots. So we don't know how to find them. It would help if I had put plus 12x here. So plus 12x. Okay. So let's just get rid of those points. I typed in the wrong equation there. I just kind of wondered, like, how are we going to do this? So you don't have to adjust your window. I'm going to go ahead and adjust my window here. Just so I can see the different solutions there a little bit. Have kind of a sense of what's happening here. So I see, let me hide that point a little bit there. Okay, so let's use the trace command and let's find the nice solutions here. So it looks like I have one at -1. I like that one. I have one at -1.73. That looks not like a rational one. Okay, so I think I got 2 nice rational ones. So this one, these 2, I'm going to characterize as it doesn't look like they're rational. If you kind of hover over them, hit the plus sign, you'll see there are way more digits. Those don't seem nice and rational, but these 2 are really nice. So, right, so I have a solution at x equals -1 and x equals 5. It doesn't matter the order here, but what I want you to do is take this and we're going to synthetically divide out the -1 here. So -1, and it should be remainder 0. So we're going to have 1, -4, -8, 12, and 15. I should get a remainder of 0 when I do this. So I get 1, -1, -5, +5, -3, +3, 15. I'm not sure if this is going to work. Oh, it does. -15, 0. Phew, remainder. Now here's the thing. We want to divide out this next root as well. So we want to divide out this one as well. Don't start over with the original problem. Start with our answer there. So we've got now, and by the way, this is going to stop. That's the remainder. So that's not part of this. It's not part of this answer. So I'm going to pull out a 5 now, and that should be, I'm going to synthetically divide out a 5. It should work out here. So this would be 5. Well, like this, 0, 0, -3, -15. Oh, that works out nicely, is 0. That's the remainder. This is the constant, this is the x term, this is the x squared. So the quadratic that's left over, which is really where we're headed for this, x squared minus 3 equals 0. I know 2 of my solutions already. I got those from the graph, but I want to get the exact values for these. Remember, they were decimals, -1.73, 1.73. Let's get the exact value. Add 3 to both sides. take the square root of both sides to solve for that one. Don't forget plus or minus. And you get x equals plus or minus the square root of 3. And if you're kind of wondering, remember that 1.73 number right there? If you go to a calculator page and just type in square root of 3, of course we want the positive negative. I'm going to put decimal so I get a decimal. 1.73205. In fact, if I mouse up there, you can see it's even more digits, and that still is rounded off there. So those are definitely the values we saw on the graph. Notice I want the exact answers. I don't want the values from the graph. So get rational answers from the graph. Don't get these answers from the graph. I don't want the 1.732 number. I want the exact answer. I want square root of plus or minus square root of 3 there. Go ahead and try your homework. We are going to spend more time on this section or sections like it, very similar skills, when we get back from the break. So do your homework, get that taken care of and knocked out.